Hi, we're back. We've been talking about what makes a planet habitable. And we just did a long thing about the temperature of a planet, how it keeps itself in the right range and moderated, and then the chemical elements, how they got there, how they're maintained available for life. And I did a long segment on carbon and water being the basis of life, arguing against alternatives like silicon instead of carbon, or ammonia instead of water. And then I talked about how the conditions of the star that provides the radiation and, you might say, the warmth change. The sun has changed its output over its lifetime, and at a time when it was a lot weaker in its output, our greenhouse effect on the surface of the Earth was a lot higher. It almost got negated when cyanobacteria started making oxygen, destroying the methane greenhouse. But there's another little tweak. There is a long-term trend in cooling. The ice ages are a fairly recent phenomenon in the history of the Earth. And I would say that modern life is still resetting the thermostat. And how is that? Okay, plants take up carbon dioxide from the air, and they put that into more reduced carbon compounds. You name it, cellulose, proteins, and so on. And then a lot of that decays back, goes back into the air as carbon dioxide, but not all of it. Some of it gets deposited in carbonates in the ocean, and that takes geological times to recycle back by plate tectonics. But carbon-based plants also make some very resistant compounds, things like kerogens that are ultimately the basis of coal. Plants have to defend themselves, so one of the things they make are compounds like lignins that are really hard for organisms to degrade, the fungi and the bacteria. So then what? Well, most of it does get degraded slowly, tens, hundreds, thousands of years, but not all of it. And that's one of the reasons that we have oil and coal. Okay. So plants, in a sense, have been slowly burying enough of their carbon that the carbon dioxide concentration in the air keeps getting a little bit lower and a little bit lower. In the Devonian, there's evidence that it might have been 3,000 parts per million. Now, before we did the Industrial Revolution, it got down to 280 parts per million. We pumped it back up to 400 plus parts per million. That's a short-term rise, we hope. Okay. So what does that mean? It means that plants have a lower and lower rate of photosynthesis, growth, and all that as the ages rolled on. One of the adjustments, you might say, that plant life made was developing a second kind of photosynthesis, so-called C4. The plants that have this pathway have a biochemical pump in front of the first big reactions of photosynthesis. And they basically take carbon dioxide at low concentrations, as in the air, and pump it up to high concentrations inside their cells. So they can get by at much lower carbon dioxide levels. They don't need as much nitrogen. They don't need as much water. But they're not the dominant plants on the Earth. They're common, but they're not the dominant ones. So there's a little quandary for plant life. Then we've got all the other elements that life needs. Us, our friends, the plants, you name it. So what are the essential elements for us? Okay, we can name the big ones. There's nitrogen for proteins. There's phosphorus for so many things, including DNA and energy currency. There's calcium for our bones. There's sulfur for some critical proteins. There's sodium, chlorine, potassium for what's called osmotic balance and nerve function. There's iodine for our thyroid function. There aren't many animals that need iodine as far as I know, and I don't know of any plants. Then we've got, let's see, what am I? Chromium, cobalt, iron, iron for our blood, zinc, selenium in some special proteins. Have I named them all? Manganese, copper. All right. And then if you take some other organisms, you have to throw in boron for plants, silicon for some plants. It's mostly defensive. Vanadium, molybdenum, and tungsten. The molybdenum and tungsten are important for organisms that fix nitrogen, the gaseous nitrogen in the air, and make it into reactive nitrogen that can be used by all other life forms. Of course, we now supplement that industrially, but that was the key to a lot of life before we started doing the industrial stuff. All right, so we were lucky then that we had a supernova or a neutron star merger that was close enough to us that it seeded the whole solar nebula with all these elements. And the story of the nucleosynthesis of all these elements is really fascinating. It's an incredible triumph of physics, how it was figured out from basically lab experiments on Earth, saying, how does the cosmos get all of these interesting things? Now, I did mention that the iron mostly got locked up in the red beds that are visible in places like the Grand Canyon. What is it? 800 feet, 200 and maybe 50 meters of iron bands. That's a lot of iron. That almost took out all the iron that was available to us. And that's where, as I mentioned earlier, that deserts come in, because desert sands with iron blow into the oceans and keep them somewhat productive. Remember, the oceans are not nearly as productive, especially per area, as the land is. The land has a much better shot at it, especially at getting iron. So let's take on that for a minute. What can life on Earth, on the land, do that life in the oceans can't? Well, it has as much trouble getting soluble iron as life in the oceans. But there are a couple of techniques. Plant roots can excrete either acids to dissolve the iron, or these things called siderophores that glom onto the iron to make a compound that's mobile. That's not possible in the ocean, because everything mixes away so fast that, first of all, it couldn't possibly create enough acid or chelators to move iron, and even if an organism did, it would only be benefiting all of its competitors. So the ocean is a tough place to make a living. I'm going to have a little leader in here, because I did say that I would give some more details, and that's about radiation as being the way that the planet and the star exchange energy. Okay, so we are situated at 150 million kilometers, about 93 million miles on average from the sun. And the sun is pretty hot. It's at 5,800 Kelvin, which is around 5,500 Celsius, about 10,000 Fahrenheit. That radiation is electromagnetic radiation, comes to the Earth, and the Earth reflects about 29% of that. So 71% gets absorbed. We can go through a little bit more of the calculation later, but that is enough to raise our radiative temperature to minus 18 degrees Celsius, about 0 Fahrenheit. And with the greenhouse effect, that gets us to a livable average temperature on Earth of plus 15 Celsius, 59 Fahrenheit. The albedo, this amount that's reflected, is important for all planets. Let's see, we've got about a minute. Mars absorbs a bit more. It only reflects 22% of its sunlight, but it's 52% further away from the sun than we are. And if you work through the math, it ends up having a radiative temperature that's pretty low. I think it was 200. Here we go. Radiative temperature of 212 Kelvin. It has carbon dioxide as a greenhouse gas, so the average temperature is 218 Kelvin. That's minus 55 degrees Celsius. We're getting down toward dry ice temperature. So anyway, we're just about at the end of this segment, and join us again next week. I'll have a guest, and I still haven't picked that person yet.